Hello, Uggies Worldwide. I'm Dave Casler, amateur radio call sign KE0OG. I wanted to comment on a question from Kevin Hastings, Victor Echo 9 XYZ. Interesting call. And up in Canada. Now, he has an old Mosley TA33 HF beam. These were beams that, the design is 50 to 60 years old. They're standard, they're well understood, there's parts available for them. You can run them forever. They're not as fancy as some of the newfangled beams, which do not have linear spacing, but it's a classic antenna. He says he has very good resonant dips for the bands he wants to be on. The SWR matches on all the bands. Why does the resonant point change when I attach additional coax to check it with my antenna tuner? I've seen this at the tower splice box. When testing the SWR, I thought that the antenna showed a good 50 ohm match with a good 50 ohm feed line down the tower to the connection box. Adding another short length of 50 ohm cable to the antenna analyzer wouldn't matter. If the antenna is 50 ohms, any length 50 ohm cable should present a 1-to-1 SWR to the transmitter, right? Right. It turns out there's a piece of software. It's a little piece of software. It's old. It almost looks like an old DOS piece of software, but it comes with the ARRL antenna book. Now, that book used to have a CD in it with all this extra software, but now you go online and download all the downloadable things to go with the antenna book. It's a very interesting piece of software about transmission lines. And what we're going to do, excuse me, what we're going to do is look at one of these scenario with transmission lines and see if the transmission line could in fact be having anything to do with it. So, TLW, let's take a look. Okay, so this is the program, Transmission Line for Windows, and written by N6BV back in last updated in 2014. Now let's pick a standard cable type. It won't matter what, but let's just take, let's say it's RG213 because this is a cable a lot of people use. Its characteristic impedance is actually 52.2 ohms and a tiny touch of, let's see, it's minus, so that would be inductive reactance down here. Have I got that right? I may have that backwards. Doesn't matter. It's so little. The matched line loss is 0.252 per 100 feet. Now, if you've got a tower out there, let's change this to 200 feet because it could very well be that long, okay? Now, if we have a load that is pretty well matched, let's take a nice load for that antenna. Let's say 60. We got to make it a little bit off. Reactance minus 37 ohms. Okay? Now, we take a look down here at the bottom. The SWR at the line input is 1.79, at the load 1.93. Rho is the reflection coefficient. What is reflecting power? What's reflecting power is this little reactance right here. Now, the additional loss due to the SWR is less than 0.2 of a dB. The total line loss, including the resistance in the line, is 0.6 dB, so it's very little. So the impedance at the input is 29.83 plus J, 6.21 ohms, or 30 ohms at 11 degrees. This is going to give you a pretty good SWR, 1.8. Okay? Now, what I'm going to look at, keep that 1.79 number in mind. We're going to add some length to this coax. We'll make it 230 feet. Okay? And look what happened at the line input. 30 feet we added an undetectable difference between what it was at 200 feet and what it is at 230 feet. Let's go radically the other way, just for kicks, and go with 120 feet. Okay, 1.84. It's not that much difference. Okay, now what's happening here is the angle is changing as you go down, but the angle doesn't matter. What matters is the rho, which is the reflection coefficient. This is the percentage of the power that is reflected. Okay, that determines the SWR. In fact, you can write the formula for SWR in terms of rho. Now, you will note in the formula for SWR that you have only scalar terms. There's no phase angle to it. Now, the phase angle, if there's a phase angle to rho, and there is, it doesn't show it here, it just rotates as you move down, but the SWR stays the same. So let's try different coax just for fun. Okay, RG8, we'll take the Belden type, 120 feet, you got it, SWR, 1.88. Let's change the reactance a little bit to like 20. Okay, now your SWR is 1.47, okay? So we've got, we're doing this on 40 meters, okay? 7.125 megahertz, 120 feet of coax. And what we can do here is by putting these different types of coax in, it will give you a very precise characteristic impedance and the matched line loss. And the match, that means one-to-one match. Okay, the velocity, power, the max voltage, total matched line loss, and this is if it's matched. Well, it's not matched. We get an SWR 1.47. So the total line loss is actually a little bit bigger than this. This is not a bad match for an antenna. Okay? I had a good conversation with John, who is one of the ARRL tech experts. I haven't mentioned this a lot, but I insisted that in my contract with the ARRL for writing the Ask Dave column, that it received peer review, and that didn't mean editorial review, that meant from an engineer, okay? And he caught an error that I made where I said if you change the line length, you will change the SWR, and that's totally wrong, as we just saw. That changing the line length to put in a antenna analyzer or something like that it will affect the SWR, because remember, in antennas, everything affects everything. But it's minute, tiny, itty bitty. It's just not worth bothering about. So if it is changing, there is something else going on, okay? One of the things that you can look at is on your antenna, you've got a match between the coax and the antenna. If that coax match is bidirectional, it's the same in each direction, okay, then you are going to find that you've got a nice match. But the problem is beams are generally balanced matches, and very often in the old days with these old beams, we would connect the coax directly to the feed point on the beam, one piece either side, okay? So that's a balanced to unbalanced problem right there. What that will do is cause current to run down the outside of the coax. The best place to terminate that might be right at the base of the tower by hooking it to an lightning arrestor. That would take care of it. Another thing that you can do is put a balun at the point where your coax attaches to the antenna. And so you've got options to do. Putting the lightning arrestor at the bottom of the tower Means you don't have to climb the tower. But you still want to put a lightning arrestor right where the coax enters the house, and that should be attached directly to the ground rod. Okay. Now, will that create two problems if the thing is grounded in two places? No. But your common mode current, which is what we call the current that flows on the outside of the cable, that common mode current is going to hit a ground point right there at the base of the tower and stay that way. From there on, you're probably going to be able to do whatever you want to the length of the cable for measuring purposes. Best, I hesitate to say this because it does involve safety risk, is to put a balun at the feed point for the antenna unless it already has a gamma match, or change the feed to a gamma match, which takes unbalanced to balanced. It's built into the way the thing matches. Okay? So common mode current may be likely what's causing your problem. This particular question will appear in an upcoming Ask Dave column. So there you have it. If those who watched are enjoying this video, please subscribe. Please also click the share button, and take a look at patreon.com/KE0OG. And until we next meet, 73.